All right, let's keep counting. Now I'm going to pick 5 students at random to do 5 warm-up problems that I have on the board. And there's only 5 kids in the class, so I've got 5 kids in the class. I'm going to do 5 problems. Well, for the first problem, there's 5 problems to choose from. For the first problem, I have 5 options. I can pick one of 5 students. But for the next problem, one of the students is already doing one, so now I have 4 options. And then 3 for the next, and 2 for the next, and 1 for the next. So I still apply the fundamental counting principle from the last video, 5 times 4 times 3 times 2 times 1. I multiply all these things. I get 120 options. There's 120 ways that I could pick those 5 students to do a problem. This is different than the phone number problem we did at the end of the last video. Because on that one, it was like there's 10 digits, and then you can repeat digits. You can use the number 6 over and over in a phone number, but I can't keep having the same students do the same problems. They're not repeating, and that changes how this gets calculated. If I had 10 students and 10 problems, I would go 10 times 9 times 8 times 7 times 6, all the way down to 1. 10 options for the first problem, but then 9 for the second and 8 for the third. And if there were 100 students, I'd have to do this all the way down to 3, 2, 1. There'd be 100 spots, and I'd just keep multiplying over and over and over. This is what's called a factorial. Factorial is when you multiply numbers in descending order, like from 5 down to 1. If I do 5 times 4 times 3 times 2 times 1, that is called 5 factorial, which is written with the exclamation point. So 5 factorial means this. It's part of fancy counting. It needed its own little symbol, 5 factorial. If you're a really cheesy math teacher, like I am, I would call this 5 because you're yelling. And so this here is 8. And that means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And luckily, your calculator can handle this. On my calculator, if I press number 8 and press the math button, and here's probability, I scroll over to PRB, here's factorial. 8 factorial is 40,320. I'll do 3 factorial. 6, 3 times 2 times 1, obviously, and 9 factorial. It's important to note that 9 factorial is really just going to be 8 factorial times 9. If I do 40,320 times 9, I get the same thing, because 9 factorial is 8 factorial times 9. This was 362,880. 0 factorial, this is a little bit odd, but pretty important. You have to understand that 0 factorial is 1. Why? There's a couple kind of reasons for it that aren't super convincing. The main reason is it needs to be for things to work. If 0 factorial didn't equal 0, we wouldn't be able to do a lot of the problems that come up. I'm sorry, if 0 factorial didn't equal 1, if it equaled 0, we wouldn't be able to do a lot of problems that come our way, so we just have to say that 0 factorial is 1. So if there's 18 problems on the board, I do 18 factorial. Oh, too fast. Sorry, I think I broke you. I'll have to pause it and fix that later, probably. In fact, I'll do that now. Okay, we're back. 18 factorial. Is this 6.4 times 10 to the 15th? A really big number. I think it's 6 quadrillion. I think that's what that is. And back here, we asked the question, what if there was 100 problems and 100 students? Well, 100 factorial is too big for my calculator. It says overflow. Can't do it. It's just way too big. So numbers get really, really big really fast. These are factorials. Now we can go a step further. What if I had 8 problems, but there are 15 possible students to pick from? With my 8 problems, I'd go 1, 2, 3, 4, 5, 6, 7, 8. I could have 15 people do this first problem, and then 14 do the second, and 13, and it keeps on going down, but we run out eventually. I'm not going to get all the way to 1 because I've only got those 8 slots. So this is not 15 factorial. It does not equal 15 factorial because it doesn't go all the way to 1. So to calculate this easily, we get really sneaky. We say, okay, let's do 15 factorial. And I should have made this number smaller, so I'm going to have to write these out for a while, but that's okay. Here's 15 factorial. And then let's divide it by 7 factorial. Why 7 factorial? Because this stopped at 8. So if I divide it by 7 factorial, these all cancel. It's really rather sneaky. So if I wanted to find how many students there were, or how many possibilities to have 15 students do 8 problems, it's not 15 factorial, it's 15 factorial divided by 7 factorial. Still a very large number. Two 594 59200. Whew, real big. 259 million. And so what if there were 10 problems and 12 students? Well, it's going to start at 12 and keep counting down. But the interesting thing is you'd think it would stop at 2 because 12 minus 10 is 2. You'd think it'd go all the way to 2, but it actually stops at 3. Because you have to count the first student as its own spot. Like when we do 8 minus 5, we get 3. That doesn't mean that there's 3 numbers. That means there's 3 steps. There's 3 steps between 8 and 5. But if I assign the problems like 15 through 18, that's not 3 problems, that's 4 problems, because you have to do problem 15. 15 counts. So subtraction is like how many steps you're taking. But here, this isn't a game of how many steps do we take, but how many actual numbers, how many actual slots do we deal with. So it ends at 3, not at 2. So it should be calculated as 12 factorial over 2 factorial, because I want to cancel off the 2 and the 1 that would have come there at the end. I want to cancel those off. So if there's 4 problems and 25 students, I'd go 25, 24, 23, 22, 21. No, that's too many. 4 slots. Do 25 times 24 times 23 times 22. So it'd be 25 factorial over 21 factorial, because I want to keep the 25 through the 22. Here's the important one. If there are problems and n students, it's n factorial over n minus r factorial. Ignore this one. N factorial over n minus r factorial. So like here, it'd be 25 over 25 minus 4. This is called a permutation. A permutation is when you have the number of options are decreasing, and as they decrease, you have to calculate your factorials. There's another key component to permutations that we'll talk about a lot more in the next video. We'll talk about it here a little bit too. But that's it with permutations, the order matters. And let's not talk about that right now. Right now, it's like for each slot, whatever you put in the slot that follows goes down. I would have 10 here, and then 9 here, and 8 here. Or I could have n options here, and n minus 1 options here, and n minus 2 options here. It keeps going down until you get down to 3, 2, 1. Or whatever you get down to. It might not end at 3, 2, 1, excuse me. This is your formula for calculating a permutation, and you've got that in your calculator. So right here I did 15 factorial divided by 7 factorial. That's the same as 15 P 8, because there are 15 students and 8 problems. Out of 15 possible students, I picked 8 of them. 15 P8. Out of 15 possible students, I picked 8 of them. Now, the big distinction to make about permutations right now is that the order mattered, meaning you cared if you did the first problem or the second problem. If there were 8 problems on the board for you to choose from, or for you to get randomly assigned to, there's probably one that you want to do more than others, and there's probably ones you don't want to do more than others based on what you know and what you don't and what you like and what you don't like. The order that they get picked in matters, and when the order matters, that is called a permutation. We're eventually in our next video talk about what's called combinations, and combinations are when the order doesn't matter, and so I'll see you there. Oh wait, let me see if there's more over here. Nope, we're good.